Reservations in two-way slabs by means of yield lines. This video will deal with cases 21 to 25, and it's about concrete slabs which who has 4 fixed supports at the end. We will deal with case 24, and case 24 is a special case. 24 and 25 are both special cases, because in all the other cases we use the 30, 45, 60 rule for determining the yield lines. Case 24 and 25 is done by attracting yield lines. The hole is attracting the yield line. So the corner of the hole is attracting the yield line independent of the angle they make. And 24 is a centric hole, centric reservation in the slab. So we have the concrete slab and a central reservation in it. That means that D3 is equal to this one, and D4 is equal to D4 left and right, and the parameter D1 and D2 are the dimensions of the reservation. It's a two-way slab, so the condition is B must be between A and 2A. The maximum hole size, of course, is that DB must be smaller than B and D1 is smaller than A. The horizontal symmetry makes that B is equal to 2 times D4 plus D2, and A must be equal to 2 times D3 plus D1. So these are the conditions, and what type of hole or type of reservation we can construct with it. I can visualize it in the following pictures. It can be a small rectangular hole in the middle, or a square hole in the middle, or a rectangular hole horizontal, or a large reservation, or a vertical reservation. That's holes of this type. Let's calculate the work done by the external forces. This is equal to, when we start with the orange area, so it is D3 times D2, and twice, because you have it on the other side, and you have D4 times D1, also twice, 2 times. So that's this term, and the mean deflection is delta over 2, so that's a half of it. For the green elements, we have 4 times B4 times D3, and it consists out of triangles, so the mean deflection is 1 over 3. We use dimensionless parameters, and we know, because it's a centric hole, that D4 is equal to this and D3 is equal to that. So we fill in the different parameters, and now we can calculate the work done by the internal forces. Then we got, for the negative yield lines, we have B times delta over D3. That's the angle of rotation. We have this here and here. There's also a yield line. So we have this 2 times. On the right-hand side, we have A divided by D4, and we have it also 2 times. And what's left is the corner, and the corner yield line is projected to the north or to the other side, and you have D4 over D3 plus D3 over D4, and then we have that 4 times in the 4 corners. Fill in the different parameters, and then we say D is equal to E, and we can get M from it, and you get this formula. The bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole. The maximum bending moment without the hole, you've seen that in the previous video. It's M0 divided by Q equals to this. So the bearing capacity can be calculated and is now equal to this formula. You see that in this formula that, of course, this cannot be negative, so A must be bigger than B1, and here B must be bigger than B2. Let's give an example where alpha is 1.5, so this is 6 meters and this is 9 meters, and you have dimension of the reservation equals to half of the side, and the width is 1/10 of this side. Then you can calculate easily with this formula, because you have alpha, alpha 1, and alpha 2. You can calculate that this bearing capacity is 132. Means that making this reservation in a slab like that, which has fixed end on all sides, you do not touch the original bearing capacity. We can now make it, visualize it in a graph. This is alpha, or V over A, from 1 to 2, and this is the bearing capacity. And we have two parameters, so we keep one parameter of the reservation constant, for instance, 0.2 times A, and we vary the other parameter of the reservation. And then we can have different curves like that. You see that we should not worry directly because everything is above 100%. So that's okay. Now let's look at alpha is equal to 1.6. It's a slab like this, as this, and then we, for alpha 1.6, it's the red curve, because we go for 0.2 and 0.2, 0.2 and 0.2. So this visualization is this, and it's 103. Then for the blue curve, it's 0.2 and 0.4, 0.2 and 0.4, and you have alpha 1.6, and you see that the bearing capacity is 101. And then we have the black curve, which is for alpha 1.6, and then 0.2 and 0.6, you have 1.5.4. So now you can also have this 0.2 times 0.8. So you see alpha and alpha 1 is kept constant in those pictures, and only alpha 2 changes, so you can easily see what is happening. It's just a reservation that is going bigger and bigger horizontally. We can now study the bearing capacity formula in another way. We keep alpha constant, which is kept at 1, which is for a square slab, and alpha 1, we change it from 0.1 to 0.5, and alpha 2, we change it from 0.1 to 0.8, and you have those different curves. This is interesting us when it's more than 100%, that's fine, but when it's less than 100%, then we are interested in it, and we blow this up. Then you will see that for small reservations, you see, because we know from the red one, it alpha is 0.1 and the blue one is 0.3. So we make this element from 0.1 to 0.25. So we have again the blue one and the red one. We have again the blue and the red one. And in between are those others. So you see that for 100%, it's around here. You have an area where you should be careful. We can now go for alpha equals 1.5. We do the same exercise. We blow this area up, and you see that these are the different values that you must take care of. And then we take alpha equals to 2, and you see now the pattern, and it's always a little bit the same, that for small reservations, you have a small reduction in bearing capacity. This is alpha going from 1 to 2, and alpha 1, because we know now when you have small reservations, it can be annoying. And we draw it in function of alpha 2 from 0.1 to 0.8, and you see now that you have a range when you blow this up. Then you have a range where it is in this area smaller than 100%. And it can go even to a loss of 10%. So it's significant, 10%. So you can use those graphs to situate or to check where you should make the reservation in the slab and where you should avoid it. So this is the red area where the bearing capacity is less than 100%. So this gives you all the combinations of alpha, alpha 1, and alpha 2 that you must be careful. For a square slab, D1 equals D2. And we take alpha 1 smaller than 0.6. It means between 0.2 and 0.6, because when you approach the edge of the slab, then the method of attracting yield lines is not valid anymore, because it do not have any realistic yield lines. Then the bending moment is then the maximum bending moment is then given by this formula. And when we take the look at the bearing capacity in function of alpha 1, then we see that we have this red curve. This is the formulation of the red curve. The bending moment, initial bending moment, is m0 divided by q, is of course this, the same. And then you will see that the bearing capacity is 0 when alpha 1 is 0, is 100% when alpha 1 is 0, and it's 100% when the bending capacity is when the alpha 1 is 0.19. So that's this portion. So it means that the bearing capacity is less than 100, then alpha 1 should be between 0 and 0.19. Or you can put it in general, avoid making holes or reservations smaller than 1/5 of the slab dimension for a square element.